we're going to be working more with the rules of exponents in this section and the next. And I want to start off with the quotient rule. Let me show you probably the easiest way to work it. Here I have x to the fifth over x to the third. I'm going to write them out. So in the numerator, I want 5 x's all multiplied to each other. And then I want 3 of them in the denominator. And you know that you can cancel whatever is the same in the numerator with the denominator. So I'm going to cancel these 3 x's up here with these 3 x's below. And I'm left with just 2 x's. So that's x squared over 1, or just x squared. So you can see this. We had 5 x's up here, 3 of them down here. Take the 5 and take away 3 of them, and you're left with 2. The rule looks like this. This is simply the quotient rule. This is the only rule I'm going to introduce here. And so what we're going to do is a bunch of examples to illustrate its use. So all of these, basically, all the problems in this section will tell you to simplify and to write your answers with positive exponents. So that's what I'm going to do for the whole thing. So according to the quotient rule, I'll have m to the 9 minus 5 will be m to the 4th. Now it gets complicated for something like this. How about 9 to the 5th over 9 to the 7th? Well, this is a little bit different, because now if you do 9 to the 5 minus 7, that's 9 to the negative 2. And you're usually asked to write these things with positive exponents, or to evaluate them when you know the number. Well, how do I get out of this then? Well, I can write this as 1 divided by 9 squared. That's another kind of a quotient rule that we used for that. And then you can finish it off by writing 1 over 81. So that's one way to look at it. What I typically do, since I'm subtracting anyways, if you look, 5 minus 7 is negative 2, and I was left with 2 below. What I typically do is look for the higher power, as long as they're positive exponents, and I know it's going to be a subtraction. So since the top is less than the bottom, what I could do is cancel the top and leave a 1, and then I could cancel the 5 9s from the bottom and leave 9 to the 2nd power, and we just have 1 over 9 to the 2nd power. So now this makes it seem like you're only working, the top is the only thing that you're interested in, when that's not true. It could be you're left with things in the numerator or denominator. It just depends on the problem. So another example, suppose I have 8 to the 4th over 8 to the 5th. Once again, the 8 to the 4th on the numerator is smaller than the denominator, so I'm going to cancel the 8 to the 4th and get rid of 4 of those 8s, leaving just 1. And so my final answer is 1/8. Let's continue. Next, I have 35 t to the 7th divided by 56 t squared. Now, your normal canceling will work just like it did before. For example, I noticed that a 7 goes into 35 5 times, and 7 goes into 56 8 times. So I've simplified the numbers. So if you want, you can get started on your fraction. I'll have a 5 in the numerator and an 8 in the denominator. Now I'll work the variables. I got t to the 7th over t squared. The t to the 7th has the higher exponent. So I'm going to cancel all the t squared out, but I'm going to take away 2 from that exponent. And there you go. So there's really not much to say here except just to do as many possible examples as I can. Now you can use the quotient rule, or I prefer to use the one rule, the one rule where I can write it upside down and all the exponents become positive. Now it's easy to see that I can cancel the whole u to the ninth, take 9 away from that exponent in the denominator, and you're left with 1 over u to the 11th. Now, by the way, if you wanted to, let me call it BTW, if you wanted to do this using the quotient rule, you would have to do u to the negative 20 minus negative 9. That would be u to the negative 11, which is 1 over u to the 11th. I personally would prefer the first way, so that's the way I'm going to proceed as I do these examples. Here we have m to the negative 9 over m to the negative 3, and I'll flip it upside down, m cubed over m to the 9th. Now the exponents are all positive. I notice the higher exponent is in the denominator, so I will cancel everything in the numerator and I will take 3 away from the exponent in the denominator. I think I took away the wrong amount. I took 3 away from the numerator, so 9 minus 3 is 6. So we have 1 over m to the 6th power. C to the 7th over c to the negative 1. Well, this is a little bit strange. Now we're going to start mixing up the problems as we typically do. You can move things so that they have a positive exponent by changing them, in this case, from the denominator up to the numerator. You can change the power into a positive one. Now you don't need the 1 in the denominator anymore. So you get c to the 7 plus 1, you add those exponents, and you get c to the 8th. Try it where I use the quotient rule, like over here, and see if you don't get exactly the same thing that I just did. Here we have negative 7 p to the 3rd over p to the 12th. And for a lot of students, they confuse the negatives with exponents. Somehow the rules get mixed up in their minds. But that negative 7 doesn't have anything to do with the exponents. In fact, if I wanted to, I could write it in this format. Or even better yet, I could write it as negative 7 over 1 times all that stuff. So hopefully you won't see that the negative 7 has anything to do with the exponents if you think of it this way. I don't know if it's helpful or not. But now what I do see of the exponents is that I see that the p to the 3rd, the 3, is smaller than the 12. So I will cancel all the p to the 3rd off and subtract 3 from that 12 to just leave a 9. So when I write my answer here, I'm going to put it back together. The negative 7 was all that was in the numerator, and in the denominator we simply have p to the 9th power. Next, I have p to the 5th, q to the 7th, divided by p squared, q to the 3rd. And this is no different from the other ones. Now, when you're working the exponents, you want to make sure that the bases are the same. So when I do my exponent subtracting, I'm only going to work with p's and p's, or I'm only going to work with q's and q's. So I'm looking at this p to the 5th over p squared. That guy right there. The 5 is bigger than the 2. So I can cancel the p squared all the way off and subtract 2 from that 5. So that'll leave me with a p to the third in the numerator. I'm not quite sure I need that much of a fraction bar. Now as for the q, the same thing is occurring here. The 7 is bigger than the 3, so I can do q to the 7 minus 3. Cancel that off all the way. And I'm not exactly sure what I'm doing here. I have p to the third, q to the fourth. All that was left in the denominator was 1, and you can just write this as p to the third, q to the fourth. Next we have 28t u to the negative 2 all over 14 t to the 5th power u to the negative 9. Now, what I usually do with these problems is I move around those variables that have negative exponents. Like this negative 2 and this negative 9, I'll flip them so that one is in the numerator, so that they're different from what they were before. I'll have u to the 9th in the numerator and u squared in the denominator. Now I'll be able to cancel those like normal. For the t's, note that t itself is just t to the 1 power. Since the 1 is less than 5, I can cancel away the t to the 1 and subtract 1 from the 5 to make it a 4. That puts a t to the 4th down in the denominator. The 28 and the 14, the 14 goes into 28 twice, so that leaves me with a 2 up in the numerator. Now I'm almost finished, except I haven't cleaned up the u's. Notice that the 9 on the exponent for the numerator u is bigger than the 2 in the denominator for the u. So I can cancel the u squared out and subtract 2 from that exponent on u, and it looks like I end up with 2 u to the 7th divided by t to the 4th. So as you can imagine, these just get more complicated, but not more difficult. There's just more variables that are thrown at you. So you'll see in this next one. Oops, I made a mistake on that. Let me try again. I have 63 a to the negative 3 b squared divided by 7 a to the 7 b to the 8th. So I'll do similar to what I did last time. Anything with a negative exponent, I will change its position, but I'm not going to write anything just yet. 7 goes into 63 9 times. Between the a to the negative 3 and the a to the 7th, what I'm going to do is put the a to the 7th here, and I'll put the a to the 3 in the denominator. That will change from negative 3 to positive 3. But then the b's I can do immediately. 8 minus 2 is 6, so I'll have a b to the 6th in the denominator. And now, since those a's, you got two a's with different exponents, I can add those exponents because of the same base. So I'll have a to the 7 plus 3, and then I'll have b to the 6th. So I have 9 all over a to the 10th, b to the 6th. For my next one, we'll do 3a squared b to the negative 11 all over 18 a to the negative 10 b to the 6th. So the only thing I'm going to do right at this moment is I see that 3 goes into 18 6 times. Everything else has positive and negative exponents still hanging around. So what I'm going to do next, I'll put my 6 in the denominator where it belongs. But now the a squared is going to stay where it is because it had a positive exponent. The b to the 6th is going to stay where it is because it had a positive exponent. However, the a to the negative 10 in the denominator had a negative exponent, so I'm going to bring it up and change it to a positive 10. And then the b to the negative 11 I can bring to the denominator and make it a positive 11. And now I can go ahead and add those exponents. So I get a to the 2 plus 10 over 6. Then I have b to the 6 plus 11. So I have a to the 12th in the numerator. I have 6b to the 17 in the denominator. Next, I have 9x to the negative 5th y squared divided by 4x to the negative 2 y to the 6th. So let me do the 9, between the 9 and the 4, nothing cancels. So I'm going to leave the 9 where it is and the 4 where they're at. The x's need to change. So I'm going to bring the x to the negative 2 up. It becomes x squared. But then the x to the negative 5 I'll take down. Now the y's are already where I want them. So I'm going to cancel out y squared and take 2 away from the exponent on y. So that leaves me with the y to the 4 in the denominator. Now I'm almost done. I'm ready to handle the x's. I can cancel out an x squared so long as I change the denominator x to a 3. So when I'm done here, I have 9 over 4x cubed y to the 4th. And then one last example from this section. These do go pretty quickly, but I assume that as you go to work them, they will be more complicated and time consuming. Here's a little bit different of a look. And maybe what I'll do is, let me go off to the side for a minute and do this. If I gave you something like this, you wouldn't think twice, at least I hope by now, just switching between numerator and denominators, moving things around like so, to make the exponents positive. Well, that's what I'm going to do in this case, exactly the same thing, except now the thing that I use as a smiley face is this whole chunk, this a plus 2b. So that means I'm going to have an a plus 2b raised to the 3rd power in the denominator, and then I'll have an a plus 2b raised to the 4th power. Now, what you don't want to do is confuse your rules of exponents with those of addition. You cannot distribute this 4 through. There's no way of canceling anything here like this except to dealing with the exponents. If you looked over here, sort of as my little model, I would do this and subtract 3 and leave a 1 there. So I will do the same thing. And then you can just write it as a plus 2b, because anything to the 1 power is just itself. And so that concludes the material for section 2.3, a very quick one. 2.4 is not going to be exactly a long video either. This is the notion of scientific notation. Scientific notation was invented to make big numbers small. Let me show you what I'm talking about. I'll start with multiples of 10 anyways. If I were to write the number 20, you have no problem realizing that it's 2 times 10. 200 is equal to 2 times 100. 2,000 is equal to 2 times 1,000. 20,000 is the same as 2 times 10,000. But I want to show you a different notation. It's not going to be so evident on this one. This is the same as 2 times 10 to the first power. The second one is the same as 2 times 10 to the second power. Notice that there's 2 zeros on the 100. That matches this exponent here. And you do know that 10 squared is equal to 100. And then maybe you're starting to see the pattern here. Next I have 2 times 10 to the third. 10 to the third is 1,000. And then I have 2 times 10 to the fourth, because I was multiplying by 10,000. Basically the exponent matches the number of zeros. You ought to know that just because 10 to the fourth, you should know this from schooling that you had prior to coming to Tri-C, is when you see 10 to the fourth power, you know that that is a 1 with 4 zeros after it. So if I write 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So that's 2 with 15 zeros after it. That's the same as 2 times 10 to the 15th power. So the idea is to take a very long number and make it very small. You could imagine something like astronomy would be interested in calculations like this because their numbers are always so giant. So this is all this is doing for you is taking long numbers and making them shorter. So we're going to work with this. There are certain rules, though, on how you can write your answer. Perhaps let me show you with an example. Let's start with 52 million. Okay, I want to write this in scientific notation. So if I want to do that, then notice that I have 52 and 6 zeros. So you would think this would be the answer. Unfortunately, it's not quite the answer. The way that scientific notation works is this. The way it works is you want a digit, a decimal, and then the rest of the digits after the decimal, and then you apply your power. So let's take a look here. My 52 million, if I were to take and put my decimal between the 5 and the 2 instead of between the 2 and the first zero, I won't have 6 places, but I'll actually have 7 places to move. Just to show you what I'm talking about, if you take 5.2 times 10 to the 7th, it tells you to take your 5, your period, 2, and to move it to the right 7 places. 1, there's one spot, but then 2, 3, 4, 5, 6, 7. You fill all those spots in with zeros, and that's why it's 10 to the 7th and not 10 to the 6th. This is not permitted. Not permitted. This is the version that we want. So the way it looks like is we have one digit, and then the rest of the digits. And that'll be times 10 to some power. That's the version that we want. So one digit, and then dot the rest of the digits, and then you figure out the power that you need to move the decimal left or right, just depending on what the problem specifies. So let's do an example now that I've sort of indicated what you need to be looking for. So let's convert 638,000 to scientific notation. So the way I do it is I put my numbers out. There's my 638,000. I need the decimal to appear here. So my answer is going to be 6.38 times 10 to some power. Well, what power is that? Well, how many places did I have to move to get here? Well, if you take a look, there's a total of 1 digit, 2 digits, 3 digits, 4 digits, 5 digits. So the power is 10 to the 5th power. Let's try again. Let's write 38.25 in scientific notation. So for this one, I want my decimal to appear after the first digit. So I need this decimal to come and be in that spot. So how many spots did I move? Well, 1 digit. And so my answer is 3.825 times 10 to the 1. And of course, you don't have to write that 1 if you don't want to. You can, although I don't see anybody marking you wrong for that, I'd play it safe and write times 10 and leave it at that. Next, let's do 62,000 in scientific notation. So once again, 62,000. I want my decimal to appear there. I have a total of, the decimal was behind that 0, so I have a total of 4 digits. So what do we have? 6.2 times 10 to the 4th power. So what I don't want you to lose track of is that this 10 to the 4th is literally 10,000. So this is no different than 6.2 times 10,000. So nothing special about those exponents. I think students lose a little bit of sight exactly what all this stuff stands for, and they're trying to maintain the look of the problem instead of understanding what's going on inside of it. Now, scientific notation was also meant to handle very, very small numbers. Let me show you what I'm talking about. Here I have a number that is really small. So what I want to do is to write that in scientific notation, I still have to put my decimal point right there. So my answer is still going to look like this. But what is now the exponent? Well, now it's a little bit different. You had to move, to go to that spot, you had to go 1, 2, 3, 4, 5 places, but this time you had to move the decimal to the right 5 places. So it's not going to be a 5. Since you moved the other direction, it's going to be a -5. And you think about this. Let me show you in a little bit more lengthy terminology here. You should know that 10 to the negative 5 looks like this. 4 zeros with a 1 after it. And then you have 9.6 times that. But whenever you're told to work with something like this, you're told that you've got 1, 2, 3, 4, 5 digits to move your decimal to the left 5 places. So this would equal, so I have my 9.6, but then I would go to the left 5 places. 1, 2, 3, 4, 5. There's my new decimal. And you can see that it matches up with our original problem there. So moving the decimal to the right is the job of positive powers of 10. Moving the decimal to the left is the job of negative powers of 10. So when you're doing the scientific notation, you seem to be moving in the opposite direction. So when I had to make this, to put my decimal point between the 9 and the 6, I had to count to the right to move it, if you will, so that it was between the 9 and the 6. But since I had to go in this direction, which was the opposite of what we were doing before, it's negative. So let's do an example. Let's convert 0.00418 to scientific notation. So I think it's not a bad idea to space it out some to make it easier to count. Okay, the way the rule is, you want one non-zero digit and then the rest of the digits. That means that I want my new decimal place to be here. 1, 2, 3 places. So this one, 3 digits is what I want to move. Since I move to the right, I'm going to have a negative exponent on 10. So I have 4.18 times 10 to the negative 3, since you moved 3 decimal places. So remember, this is always what you want to have. The decimal must fall after the first non-zero digit. Next, let's convert. This time I have a negative number, negative 0 point, and I think I've got a total of 5 zeros. Let's make it 6 zeros. 1, 2, 3, 4, 5, 6, 2, 2 to scientific notation. So this time, let's put, well, the negative, by the way, the negative is thrown in there something of what they call a red herring. It doesn't do anything. It's not in any way, shape, or form connected to the exponents at all. So the negative, it doesn't even play a role in here other than to just be there for the rest of the problem. Let me write out all my digits. 2, 3, 4, 5, 6, 2, 2. My decimal needs to be between the twos. So I had to go a total of how many digits to make that happen? 1, 2, 3, 4, 5, 6, 7. 7 digits. So we know that I have 2.2 times 10 to the negative 7. $990. Well, this is pretty easy. I need the decimal between the 9s. So that's going to be 9.9. And since I had to move this time the decimal to the left 1, 2 places, this is times 10 to the positive 2. Don't forget your little x in there. let's convert negative 550,000 to scientific notation. All right, so I'll write it out. Remember, the negative doesn't have any bearing on what you're going to use as an exponent. Notice the decimal is there, and I need the decimal to be here. So that's a total of, let me see what we got. I really screwed that up. Let me fix that. So how many digits does this encompass? We've got 1, 2, 3, 4, 5. It's got a total of 5 digits. And since I had to move the decimals to the left, we're going to get 5.5 times 10 to the positive 5. So probably one thing to keep in mind while you're doing this, to maybe keep track of yourself, is negative exponents mean tiny numbers. Positive exponents mean big numbers. Then you have a couple of problems of this nature. Here I'm going to have 8 times 10 to the 7th divided by 4 times 10 to the 4. Well, we just did these kind of problems. Between the 8 and the 4, I can cancel because 4 goes into 8 twice. Now, between the 10 to the 7th and the 10 to the 4th, I can cancel the 4 all the way off and subtract the 4 from that exponent. So what am I left with? All I have in the numerator is a 2. Don't cancel the times signs. Leave those in. The denominator was just 1, so I'm not going to write anything there. So you can even, there's sort of an arithmetic that you can use here as well. Look at the next one. For my next one, I have negative 3 times 10 to the negative 2. And I'm going to take that and multiply it to negative 2.6 times 10 to the negative 3. Now what you can do in a problem like this is you could multiply the 3 and the 2.6 together. So let me do 3 times 26. See, 3 times 6 is 18, carry the 1. 3 times 2 is 6, plus 1 is 7. So it looks like 78, but don't forget there was a decimal place here. So I'm going to have 7.8. Now the negatives, of course, negative times a negative cancel. I have 10 in both situations. So I'm going to have 10 to the negative 2 plus negative 3. Since they have the same base, you do this. So this is 7.8 times 10 to the negative 5. Let's do another one. Here I have 4.7 times 10 to the negative 3 plus 8.8 times 10 to the negative 3. Well, notice that I can factor out the negative, or the 10 to the negative 3, and I'll have the following. 4.7 plus 8.8 times 10 to the negative 3. I could use the distributive property for that. And now I can add these two things together and I'll get 13.5. Now, while that's the correct answer, it's not in scientific notation. Change to scientific notation. So just in case you're forced to put the final answer in there, remember my answer has to be like this. My decimal has to be between the 1 and the 5. There's no choice about that at all. So what happens to this? It's certainly not going to stay the same as it was before. So how would you get this decimal to move to the left? Well, when we moved it to the left, we added to the exponent. So I'm going to change this to a -2. And that will make it work out. Let me show you what I'm talking about. Let's do 13.5 times 10 to the -3. That's 13.5 times 0.001. Now, accordingly, when you multiply times something like this, you move the decimal to the left 3 places. So I'll be left with 0.0135. Now look at this version of it. 1.35 times 10 to the -2 tells me, well, let me go ahead and write one more step. And then you know to move the decimal to the left twice now. So we have put 1, 2, and we're left with 0.0135. So you see they agree. This number, which was not in scientific notation, in this version it was. So what did I do here? When I moved my decimal to the correct place, this changed by one integer, I guess. I added 1 to this exponent. If I had to move the other direction, I would subtract. So be careful with that. You might, perhaps, you might have done this, multiplied it out like this, and then you get this, and then you get this, and then you notice that you have to move the decimal into this spot. So there were 2 digits there that you had to move. And then that would tell you that you have 10 to the -2 power. Here I'm going to do 65 times 10 to the second, and I'm going to multiply that to 38 times 10 to the 8th. Now, what I can do is I can do 65 times 38. Let me go ahead and do that. 5 times 8 is 40. Let me carry the 4. 6 times 8 is 48. With the 4 is 52. Then 3 times 5 will be 15. So there'll be, and I'll carry the 1. 3 times 6 will be 18, plus 1 more will be 19. And let me finish it off here. So I'm going to get 2470 times 10 to the, I have a 10 to the 2 and a 10 to the 8, so 2 plus 8. Now, which way to move my decimal? Well, I need my answer to be 2.47 times 10 to the something, because I need my digit to be between the 2 and the 4. How do I do that? Well, when you look at it, I had to move from this spot here, right before the X, 3 places to the left. Now, remember what that did up here. When we took, where was it? When I had to move my digit to the left 1 unit up here, I added 1 to the exponent. So if I move to the left 3 places, I have to add 3 to the exponent. Another way to look at this exact one, let me come back here. Maybe this might help you. Maybe it will help you to think of the 2470 as 2.470 times 10 to the third, because that way that would move the decimal to the right 3 places like you want. But then you still have a 10 to the 10th. So when you add the exponents on the tens, you get 2.47. You don't need the 0, times 10 to the 13th power.